Yeah, so also welcome from my side. So after, we consumed a lot of hydrogen now, so now we can produce some hydrogen or some green hydrogen, and we kind of turn the technology upside down to now end up at the electrolyzer. And maybe if you've heard of FEV, that's not the first thing that comes to mind, is electrolyzers. So, but within our sub-brands, we have also the sub-brand FEV Energy, and in that part, at FEV Energy, at the pillars we have there, we have, for example, Power to X, which is something that I presented here last year on a very high level GTI model on a complete Power to X plant. And there our outlook was that we want to look into more detail on specific technologies within that Power to X range. And of course, that's why I'm here today. We took the last year to really dive into electrolysis. And the system modeling is what I want to present here. And of course, with FEV propulsion, we've been using GT for lots of years, and here we can really use the same methodology that we use for combustion engines, also fuel cell, of course, and now in between that Power to X field and fuel cell, we now have also electrolysis modeling. Since for most of you, I guess it's the wrong way around, the technology, I thought I'd bring a few slides to visually kind of sum up what electrolysis, where it differs, especially since we'll be looking at alkaline electrolysis, so not PEM electrolysis. There are some more differences which are key when simulating it as well. So maybe I'll start here with the two options. We can do it in an alkaline environment or an acidic environment where we have the PEM electrolysis, and now we want to split our water. So now we put in electricity, so energy to split our water. We need the contact to the electrode. Ideally it's coated, so we need less energy to actually split the water to activate that reaction. And then we have on the left side for here the anode, and on the right side the cathode. So the first thing we'll notice that for the two technologies, the water comes from different sides. So on the one side, on the alkaline environment, we actually provide the electrodes to that side and kind of rip off that hydrogen, whereas on the PEM side, we would kind of, the hydrogen atom would kind of provide its electron there. So we at both end up with H+, but now in the alkaline, we actually have that negative charge OH ion. And now that we need a separator to get our product separated, we now, instead of a PEM, have the porous separator here within that liquid KOH and water solution in the alkaline electrolysis. And now our larger, heavier OH charged ions have to move through that porous layer instead of just the H+ ions on the PEM technology. And there on that side, then they can recombinate, and we have then hydrogen on the cathode side, and we actually produce water as well. So from two water on the right side, now we also have water on the left side, and are in that liquid state. And as we can also see that we have this gap between actually the electrodes and the separator, which is something that we don't really have on the PEM side here. We really just have to get through the membrane. Now at the top, we actually need to get through a lot of water or KOH solution with water. So that's one of the key differences, because now that we generate some gas in here, we actually have the bubbles forming. So through where our OH minus ions have to travel, we actually now have bubbles in the way. The higher the load, the more bubbles we produce. So that's actually something to also consider in the simulation, that it kind of takes away some space for the OH to travel, and that we need to get rid of all those bubbles quickly. And something we know from also the fuel cell, the PEM, that there we need at the bottom in orange some sort of current collector, since we cannot actually directly get the contact at the electrode. On the alkaline technology, it's often just that the electrode is on those flow fields. So here we don't need any current collector in that sense, but of course we have to cross through all that liquid electrolyte. So that maybe as a summary on the top technology, how it differs and what are the key aspects. So we have that gap between the porous separator and actually our electrodes. We have the bubbles in the way. Now we want to simulate all these parts. Why do we even look at the alkaline? It's an older technology than the PEM. It still has some values, especially since we don't need any precious metals for the electrodes. and therefore it's also cheaper and very robust technology. So they've been using, we've been using all these for many years. The PEM is newer, and that's also something, since the technology is that old, before even there were simulation models, you rarely find actually that people still simulate the alkaline version. So we really wanted to have both, and for today I picked to present the one that differs the most, let's say, from the fuel cell. So then we start at different levels. We really want to go from cell to the system and look at efficiencies. Where does the losses actually come from? What's the main part? Where can we improve the most? So if we look at the cell, for example, here I want to talk about the electrochemistry, how we simulate that, use the GT electric circuits here as well. Then moving to the stack, we look at the mass balances, the gas purity, which is key, especially on the anode side, that we don't have too much hydrogen and oxygen, which is always bad if it gets too much. And to then get actually to the system, to have all the pumps as well, to take the losses into account, see how much actually on the whole system, different cell perimeters, how these losses affect the overall system efficiency and so on. And then we actually have a model that we can also run transiently, have a dynamic behavior. And for today I picked up to look at the startup process, which is something you often hear when you hear alkaline with this PEM. It's often said PEM is a bit more efficient and much faster. So that's something I want to talk about at the end. So on the cell level, we have now the screenshot on the top left again, or the picture again, with all that different stages our OH ion has to get through. And basically at every step, as we see beneath that, we kind of have to have some extra voltage to get through that. We have the activation energies needed in the red part. Then we have to get through the electrolyte here, that liquid state, and also of course the separator, which we all then simulated in this electric equivalent circuit in GT. And based on the Nernst voltage, which is our base level here, of course, also now important to mention that we not just have water, but it's actually a solution of KOH and water. So we need to take the properties of KOH into account, also come up with a new species that we created then for in GT to represent our KOH solution as well. So here on the left, we can then see how much each of these resistances kind of play into parts. So now it's basically the UI curve just again flipped upside down. So now it rises with higher current density, so we need more voltage to actually produce hydrogen, especially here in red. We now see those ohmic losses that of course ramp up once we increase the current. And here of course again it's important then now to take into account this bubble formation on the one hand side, and especially that gap that we now have between the separator and the actual electrode, that this is highly influencing the overall scale of the ohmic losses. So here in the red bar is with 4.5, and then if you see the dotted line, this is how much we could reduce it if we actually just decrease the gap between the electrode and the porous separator. So you could ask, if it has such a huge impact, why don't we just try to close it as much as possible? And here we have the bubbles that kind of, if we get too close, we just create this foam of bubbles and solution. So actually it has no way to go quickly, and we have then very high resistances. So really the bubble formation kind of limits our minimum gap, but ideally a lower gap can help us to also reduce these ohmic losses here. And then at lower loads, we can see it's that green and bluish color that is really the activation over potentials that then are leading to that increase in cell voltage. And here again, it's very crucial to also take the bubble creation into account again, since this is really reducing our active cell area if there are all these bubbles attached to the surface. So if we now have the bubbles, we also need to talk about what's the impact now that we have this KOH. And here we can see on the left for different temperatures. So the higher temperature, the higher we actually have of a conductivity. So here we want to, of course, get as a higher conductivity as possible. And on the x-axis, we can see the concentration of KOH within that solution. And here we can see that at different temperatures, actually the optimal KOH concentration slightly changes. So ideally you would even want to change your concentration if you ramp up the temperature or move down in temperature. But we can also see it's only a slight effect, that perfect matching of KOH, as we can then see on the right side in those two plots. The left of this one is varying temperatures, so here we can see a huge impact if we increase temperature, that the overall resistances go down, whereas for the KOH solution it really has like this minor dip, but there's still like a 1%, 2% increase opportunity if you match the KOH concentration correctly with your temperature. So then if we take multiple cells and to a stack, we can look at the mass transfer mechanism. So of course within each cell we have the diffusion. So we actually have hydrogen moving to the oxygen side. Now for the alkaline electrolyzer, it's actually another effect that can lead to this hydrogen on the oxygen side, is because since we just pump the whole electrolyte, that liquid electrolyte, in one path back into the cells, that we actually have also a mixing through that electrolyte, that any hydrogen that was not taken out here on the separator could end up, when it comes back, in the wrong side. So actually the mixing is also crucial to simulate, to actually get the overall hydrogen in the oxygen concentration, which then is key really now for the low load, to look at what concentrations you end up. So hydrogen compared to the oxygen on the anode side, and here it's really crucial because at around 4% hydrogen oxygen you really reach that lower explosion limit. So you really want to avoid that. Basically you often say you go to half that, you allow maybe 2% is still safe, and we can see here now that when we remove or reduce current density, we move to the left, that for different pressures we reach this 2% limit, let's say, earlier if you had higher pressures. So this really limits the minimum load you can actually operate your electrolysis at, especially if you have high pressure. You can reach that at 20-30% of your minimum of your normal load. So here you are more limited, let's say, than with the PEM technology, if you operate an alkaline electrolyzer at higher pressures. And then if we look at the system, so we now had this kind of image already, and then we take also the gas purification into account, the energy consumption here to really get high purity on the hydrogen side. We then need a deoxidizer to get the rest of oxygen out, and then again temperature swing absorption, because there's then still always this water, since we are always saturated with water, with all that water around. We need to get rid of that to really have a pure hydrogen output stream. And if we take all these energy consumptions, both for the hydrogen and the oxygen side, into consideration, we can now come up with our final efficiencies and look, okay, which part now hurt us the most. And we can first say, okay, we have the voltage efficiency. We saw that first on the cell level. We have our ohmic losses. We can take into account the Faraday efficiency, so that we had this crossover of hydrogen that we lost. Something that's also more unique to the alkaline electrolysis is that we also have these shunt currents, so that electrodes actually kind of pass by our cells and move through the piping, and so that's electricity wasted in some sense. It's also quite a big impact, something that's not as much or not really the case for the PEM electrolysis. So one of the key features here why PEM is also overall has higher efficiencies, because of also these shunt currents we have in the alkaline version. And if we multiply that, we kind of have the electrical efficiency. And lastly, if we take all the pumps and so on into consideration, we have the system efficiency. And this would then look something like this. So now we have power on the X and Y axis. So we ramp up from 0 to 2 megawatts. And the orange part is what we are left in hydrogen energy, let's say. And then the other colors is what we've lost along the way on the Faraday. So the mass losses of hydrogen, and then the voltage losses we can see have really the highest impact. To trying to reduce all these ohmic losses here is really the key part on what makes the most or has the biggest impact on the losses. And actually the system losses here in red are fairly minor, so the pumping and all that is not as significant as really trying to reduce further our ohmic losses when it comes to the alkaline electrolysis. And basically with this model, we can now try a lot of different things. I picked out, as I mentioned here, maybe on the dynamic side, the warm-up phase. As I mentioned, it's often said that the key downside of the alkaline electrolysis is that it's rather slow, which is actually not quite the case. So once both are heated up, both technologies, let's say the PEM can react in milliseconds, whereas the alkaline electrolysis can react in seconds. So still quick enough if we are, let's say, as an input use photovoltaic electricity. The sun is not going to change within seconds, so that's still quick enough. However, since we have all that water or that KOH solution, we have a lot of mass that needs to be heated up once we start up the electrolysis, and this is where the alkaline really is much slower than the PEM because of all that water and KOH solution that needs heating up. And here it's actually crucial again to have specified our own KOH species in GT, because especially in literature you often see that these kind of heat up simulations are done for the alkaline just with water. And one key feature is also, if you take KOH into account, that you really reduce the heat capacity of that solution. So it has a much lower heat capacity of around 25% lower, and that of course helps again to really heat up the whole system much quicker. And basically what we can see is, depending on at what current density you ramp up your electrolyzer, that you can have a difference of a couple of minutes just by taking correctly into account the KOH and not just the water as the base heat capacity here. And then you can say it takes about 20 to 30 minutes to heat up such an alkaline electrolyzer in the megawatt scale. So this is maybe one of the drawbacks then for the alkaline, but really only if it starts cold. Once they're both warm, PEM and alkaline can really perform quite well also transiently. Yeah, and then the conclusion is, as I mentioned, that it's really robust technology. So I think there is still value to simulate and improve it, especially if we want to produce as much hydrogen as we'll likely need in the coming years. So having that robust technology is probably a safe bet to go for. There is room to improvement. It's dynamically not as bad as often said. And for us, really on the simulation side, we really want to now, as I mentioned, often these bubble simulation, do a 1D discretization in both the separator, so dimension to really go and have the different concentrations within that separator, but also in the along the flow field to really have accumulation of bubbles alongside that path and see where, let's say, the bottleneck is with bubble transfer, that we can more accurately predict what is the maximum load at which this bubble or this foam that's being created can limit us on that regard. And with that, I'm done with my presentation. So thank you very much for your attention. And if there are any questions, feel free to ask.